Hello, hello. Okay, welcome back. We got sound. This is going to be part 2. Again, just kind of a highlight overview. Trying to keep it relevant for you guys and what you'll hopefully help you a little bit in clinic, depending where you practice. So let's just jump right into it. It's going to be a lot of what was in part 1, just definitions, kind of defining things, seeing how they're good for you guys, or how it's relevant and what may be beneficial for you guys. All right, so let's get into it. So first, risk versus odds. So in a non-statistics conversation, most people use them interchangeably, risk and odds, the odds of something happening or the risk of something happening. So that's just, in lay speak, and I'm guilty of it too. I do this all the time when talking to friends, family, or whatever. But in the statistics world, they are different. So when you're reading a paper or you're looking at any research or anything, please keep in mind that risk and odds do have different definitions. So risk is the chance of an outcome of interest divided by all possible outcomes, where the odds of something happening are the probability of an event occurring over or divided by the probability of event not occurring. So they're close, and students get them mixed up. I get them mixed up. It's easy to, but definitely keep them separate, and they cannot be interchangeable is something that sometimes people just want to take the numbers and plug them back, or just call them, same thing. So here's an example. I think that'll help. You take 100 people that smoke tobacco. 35 develop lung cancer and 65 do not. So the risk of lung cancer is 35 divided by 100. So that's 35% versus the odds of it happening are 35 divided by 65, which is 54%. So you'll notice you get two different numbers, and so it's important to be mindful of what the study is saying. Are they talking about risk? Are they talking about odds? Are they talking about both things? There is sometimes a case when they can be very close, but again, they won't be exactly the same. So when the event rate is really low, so usually less than 10%, risk and odds are very close in value. But so you may see close numbers. Maybe it's rare, but you may see the close numbers, but just always keep in mind that they are different. Even if in casual conversation, people, interchange them all the time. And here are the definitions again. So when to use risk and when to use the odds, or when is it more appropriate to use one versus the other? So it's important to think about what goes into calculating them when you're trying to figure that out. And this would be more if you were writing your own paper, designing your own study, less so if you are actually reading someone else's work. But risk requires the use of the people at risk in the denominator. So in a retrospective study, so something that's looking back in time, you cannot use risk because you don't know the total number of exposed people. So if the study is retrospective, you should use odds, or the researcher should have used the odds, where you can measure the strength of association between exposure and outcome. So retrospective, odds. I guess retro has an O and then odds starts with an O is how I remember it. However, in a prospective, which actually that doesn't, I'm thinking about that. I don't know why, but just, okay, retrospective. So things that are retro or happened before are odd is just how, think of it like that. So retrospective odds. However, in a prospective study, so something that you're looking at the future, you can use risk because the total number of people exposed is available. So, and you can also use odds in a prospective study too, because you also have that information to calculate if you wanted to. So retrospective is only odds, prospective, risk, and odds. So for example, for a case control study, which is a retrospective, you use the odds, and then a cohort study, which is a prospective, risk, or odds. Okay, now wait one sec. Okay, sorry about that. It's the weirdest thing. No one ever texts or calls. As soon as I hit record, then my phone starts blowing up. Okay, yeah, sorry, but it's my wife's first week at doing the residency thing, and the schedule it's like orientation stuff, it's administrative stuff, so the schedule's not super bad. It's like 7 to 5 this week and next week, I think, hopefully. So it's not too bad, but it is funny because she would had trouble and didn't like the 8 o'clock labs and lectures. And I'm like, hey, academia doesn't seem too bad after all, right? Maybe you should come back. Come on. But anyways, so she's going to be busy. And then she does medicine, her first rotation, and I'm laughing and it's evil, but they start rounding at 5:45 a.m. So I was like, yeah, 8 o'clock compared to 5:45 a.m. Doesn't seem that bad. But anyways, so we have relative risk here, just changing gears completely, aka risk ratio, and aka Rick-roll ratio. That is made up. So cross that out. I'm lying there. Let me take it off the slide. Okay. And this is the probability of an event occurring in the treatment, which is the exposed group, versus the placebo, so non-exposed. So who gets the drug and who doesn't get the drug, for example. And this is usually expressed as a ratio and then converted to a percentage. So here's an example. We have a drug named AO, and we're comparing it to placebo. And this helps, this new medication that I made up is going to help with hypertension. So 9% of patients taking drug AO developed hypertensive urgency compared to 28% of the patients in the placebo group. So the relative risk would be the treatment event rate divided by the control event rate, or the incidence of exposed subjects divided by the incidence of unexposed subjects. So those both are relative risk. So either way, for this example, it's going to be 9 from here, 9% divided by 28, which you get here, and is going to equal 0.32 or 32%. So it's saying, you can say then patients taking drug AO are only 32% as likely to develop hypertensive urgency compared to placebo. So, and then you can go a step further and calculate the relative risk reduction, which is a little more to me it's more intuitive and it's easier to understand, and we'll go into that more later, but relative risk would just be the 32%. And I like how it's worded here, because some of these, like I said on the last lecture, some of this stuff is, to me, kind of backwards seeming or kind of confusing, and I have to keep revisiting it, but anyways. So relative risk is saying that if the patient takes the drugs, they are only 32% as likely to develop the hypertensive urgency compared to placebo. So you don't need a placebo group to calculate. My example had a placebo, you don't need to. You could compare the drug AO to anything else, to another drug, another intervention, a device, a surgery, for example. So anyway, so you'll see relative risk. It's not just pharmacist brain. I think of drugs and placebos. That's always, and that's in pharmacy school. They're always like drug versus placebo, drug versus placebo. That was the go-to example in pharmacy school. So with risk, it kind of has a negative connotation. So it's typically to interpret or to kind of predict or interpret the likelihood of unfavorable events. So the previous example, the hypertensive urgency is an unfavorable event. Most people can agree to that. So you can also compare incidence of unwanted side effects in treatment group versus control group. You'll see that in the drug studies too, with relative risk of, how likely are they going to get vomiting or nausea or rash or whatever. So think of the job of relative risk is to compare the likelihood of an unfavorable event occurring in one group versus another. So how likely are you going to have a bad side effect, for example? It can also help determine statistical significance, which remember we talked about before. So if they have a relative risk of 1 divided by 1 equals, because math, basically, sorry, that was a smart ASS answer. But that means that there's no difference between the treatment groups if it's 1 divided by 1 equals 1. So if the confidence interval for relative risk contains the number 1, then the results are not statistically significant. And then if you have a relative risk less than 1, that means that the intervention reduced the rate of an unfavorable outcome. Again, because of math. Sorry, put that twice just to entertain myself. Sorry for all the sass on these slides. So if the treatment group above was 32% less likely to develop hypertensive urgency, because 0.32 is less than 1. And then on the other hand, if relative risk is greater than 1, this means that the risk was increased with the intervention group. So just to summarize, and just so it's all on one slide, nice and neat. Relative risk less than 1, reduction in rate of, let's say, adverse effects, something that's unfavorable. Relative rate equals 1, that means there's no difference in the outcome, and it's also statistically insignificant. And then a relative risk greater than 1, you have an increased risk of a side effect, let's say. So you have to be careful, though. The one caveat with relative risk, it is one of the weaknesses, is that it can overinflate the treatment benefit of a given group. So you may see people kind of highlighting that, but just know that it is a weakness, and it's not something to overly kind of look at, overly tout. You want to look at it, but it is something that be a little bit, like I talked before, have that professional skepticism and really try to look at the full study, and not just look at one thing. Don't just look at relative risk and isolate it kind of with blinders on. So then odds ratio is kind of like the cousin, I guess, of the relative risk. And they are confused a lot by students, so definitely keep their definition straight and what they're used for, etc. So odds ratio is a comparison of odds in two different groups, and just the ratio of two different sets of odds. And it's typically used for retrospective studies, such as case controls. And then we can use the confidence interval of the odds ratio to determine statistical significance. So it's a lot like I said, like the relative risk. So if an odds ratio is less than 1, exposure associated with lower odds of outcome. If it is equal to 1, the exposure does not affect the odds, and it's statistically insignificant. So again, like RR, the risk ratio. If its odds ratio is greater than 1, exposure associated with higher odds of outcome. And just note too, it's like the relative risk that if it crosses 1, or if it has 1, then it's statistically insignificant. So here's a visualization of the two relative risk and odds ratio. So you could, you'll see these in studies, and you could set this up yourself. I'm not going to make you guys do this. We had to do this in school. It wasn't fun, but this is a good way to visualize and maybe help you remember the odds ratio versus relative risk. And you can set, and basically set these values here, and then they correspond here into the equation. So that chart before is, I think, a useful way to visualize and to see the differences between the two. It can also make, if you do need to calculate the odds ratio or relative risk, it does make it easier to do, or for me, because I'm visual, there's visualization here. And then just read through this, but yeah, this is basically showing how to use this chart. So then there's triple R, relative risk reduction. Make sure I say that slowly so I don't trip up. But this is how much the risk is reduced in the experimental group compared to the control group. And it's easy math. Woohoo! I like easy math just as much as you guys do. Oops. So you could take the relative risk and subtract it from 1. So it's 1 minus relative risk. You run into this a lot in medical literature, so you will see this if you're reading journal articles, etc. And it's usually easier to understand than the relative risk. So because with the relative risk reduction, you're getting a percentage increase or decrease, and so this is where you'll see things that this medication lowers my chance of heart attack compared to placebo, and this is where you get this relative risk reduction is what they're talking about. There is a weakness though, and it doesn't tell you anything about the if the study can be generalized or not. So how much does the results apply to the population at large? How much does it apply to your patient population, geographically, etc.? And this means that the relative risk reduction tends to overinflate the treatment effects of a given intervention. So is this why it's used more? Illuminati? No, the Illuminati thing is a joke. But is it really? Again, kind of having that professional skepticism, that professional cynicism. Just be mindful when you're getting a relative risk reduction. It kind of sounds too good to be true, and that's all they want to talk about. Again, it's just this one thing. And just in general, you probably notice a trend here with when you're looking at a research paper, if someone else is presenting it to you and they only want to talk about one little kind of corner of it, they don't want to just sort of talk about and look at the whole study, then that could be a red flag of like, you only want to talk about the relative risk reduction. They're like, yeah, don't worry about anything else. Just again, be mindful of, can this be generalized? This this claim that you're making can be generalized. Oops, I don't. Okay, that wasn't one sec. That's better. Okay, another shout out to Tim and Eric. Okay, and so in order to measure the effect of the population at large, you need a different number altogether. So you need the absolute risk reduction. So the relative risk reduction only applies to the study population of the paper you're reading. And that's where, although your morning news will not tell you that, so you get a lot of, I wouldn't recommend getting your scientific knowledge and healthcare knowledge from the morning news, but they like these relative risk reductions, and they'll sometimes, again, run with it and kind of overblow things. And so, again, is it generalized or not, right? This is the big key thing. I would be highlighting and starring this if I had my stupid highlighter thing working. But so that's the thing you have to be mindful of. Definitely red flags all around if they're kind of all they're talking about is a relative risk reduction, and they are making it seem like it's, generalize, that you can generalize to the entire population. So because if you want to make a generalization to the population at large, you need to calculate the absolute risk reduction. So put a star by that. That's important. And here we go. So the relative risk reduction, it measures our risk of something compared to something else. The absolute risk reduction is the risk of something compared to something else while accounting for the actual likelihood the event will happen in the population at large. So the ARR is generalizable, and it doesn't have that weakness of the relative risk reduction. Okay. So I think the example would help here. So drug trial, drug X compared to placebo on the incidence of stroke. And throughout the trial, the incidence of stroke in drug X group was 2%, while the incidence of stroke in placebo was 4%. So the AR is simple. You take the control event rate minus the experimental event rate, so pretty simple math. So to use the numbers above, we have 4% minus 2%, which you convert to decimals. 0.04 minus 0.02 equals 0.02. So the ARR of drugs X is 2%. So you see where I got those numbers from here, 2 and 4. So, and with the same study, the triple R would be 50%. So you could see where someone could take this 50% and really run with it. But then you'd have to be, and that would be headline news that like, oh, 50% reduction or whatever. And or 50% better, whatever, depending on how they're wording it. And it's like a bigger number. It looks a lot more kind of substantial, etc. Where the absolute risk reduction accounts for kind of the whole population at large, and it's 2%. So it's not as kind of as glamorous as a number, and it won't probably make headline news. So it's again, depending on what you work with, where you're working, and if you really are looking at these research papers, or you get something from the drug rep, and if you can calculate the ARR, and that'll give you a better idea of if this is a generalized result. So yeah, the drug reps would be super pumped with the number like 50%. And so they're probably just only going to talk about the 50%, and they're only going to talk about the RRR, the relative risk. Let's see, relative risk reduction. Where am I? Oh yeah, sorry about that. So the drug reps are going to be they'll be all over that. They'll only talk about the 50%, because it looks a lot better than 2%. So it's very advantageous to calculate the ARR. So not every study does it, and so you will probably have to do it yourself. But it's not that bad at math. So changing gears here a little bit, another important number that this will probably be in the study, or they may include this, is the number needed to treat, NNT. So it's the inverse of the ARR. So it's 1 divided by ARR. And so it's the number of patients you need to treat to prevent one event. So for example, heart failure medication, Entresto reduces your absolute risk of dying from cardiovascular death by 3.2%. So and that's it. 1 divided by ARR is 32. So in other words, you need to treat 32 patients with this medication in order to prevent one cardiovascular death. AAR and NNT are things you should calculate with every single study you read. Again, they probably won't be reported. They probably won't be given to you, but they will help tell you a lot more about the drug, for example, because they help give context and perspective to the study results, and they help you getting kind of seduced by the news headlines, the drug reps, etc., with the RRR being, for example, the one we just talked about being 50%. Number needed to harm, it's the evil brother of number needed to treat. So this is the number of patients you would need to treat to cause a bad outcome. So it's a measure of adverse effects as opposed to treatment benefits. It's calculated the same way as NNT, but instead of AR, we use attributable risk, AR. And attributable risk is very similar to absolute risk reduction. So, and you'll remember this formula from earlier, but attributed risk is identical, except that instead of dealing with event rates, you're dealing with exposure. So it's calculated by subtracting the incidence of individuals exposed to the risk factor minus the incidence of individuals not exposed. So this is a little setup here. So let's go through an example. I think that'll make it hopefully more clear. So example of bradycardia being caused by metoprolol. So bradycardia in patients taking metoprolol minus bradycardia in patients not taking metoprolol. And then the number needed to harm would be 1 divided by that AR. Switching gears again, hazard ratio. A hazard ratio here is a negative outcome. Death is typically the one that they're referring to when they talk about a hazard, but it could be anything else that's undesirable. So adverse effects too sometimes, or making a disease worse, or causing a cancer tumor to grow or whatever. One sec. Okay, sorry about that. My wife's, I guess, has a break or whatever, but so she's texting me like crazy. Where was I? Totally lost my train of thought. Oh, so hazard, death. Typically, but it can be other things. Okay. You see it a lot, like I mentioned, with the tumor size growing or the cancer becoming worse. You see it a lot in oncology literature, if you guys are going to be reading that, depending on where you practice again. And so the ratio implies that you're measuring the rate of this negative event in one group compared to another group. So getting one chemotherapy versus another, let's say. So it's similar to the odds ratio and the risk ratio above, and the hazard ratio of 1 means that there's no difference between the event rate of the two groups. And the hazard risk ratio less than 1 means that there is a low risk of the negative event occurring in that group. And then if it's greater than 1, it implies a greater risk. Correlation. So this is, again, sometimes it's used in casual conversation, but it has maybe a little bit different definition and a more specific definition for statistics or the statistics world. But it's a measurement of relationship between two variables. And this you typically see with these scatter plot graphs where the line going through, this line of best fit, and where there's one variable on the x and y axis. So you'll see these a lot of times with correlation. And you'll notice there's a positive correlation that goes this way, goes up and to the right. The negative correlation slopes down here, and then no correlation would be where the scatter plots aren't really scattered. And there's mathematical formulas to do this and kind of determine. But anyways, and then depending on your variables too. So when you see these in studies, you'd want to look at the x and y axis and see this positive correlation. So it'd be this time versus exposure, let's say, and then so over time you get more exposure, let's say, versus over time there's maybe less exposure, I don't know, or just they can't make a correlation. So it's important with with these graphs when they're presented in studies, to definitely look at them, look at what type of correlations they're showing, and then also make sure you definitely read the X and Y axis and understand what they're trying to describe. So it's a line that's usually distilled down to a single number, and it's called a correlation coefficient. So there's a whole bunch out there in the world of statistics, but for clinical literature, you just need to worry about the Pearson correlation coefficient, which you'll see abbreviated with the lowercase r. So it's lucky for you guys, you only have to worry about that one. And then the Pearson correlation coefficient ranges between -1 and 1, meaning that you can, wait one sec. That was weird. It was, for some reason, my computer's like, the screen was cutting that off. But that you can measure both direction and magnitude with it. So if R is 0, then there's no correlation between the two variables. And that's the one on the right. So that image up here, that's the one right here. This is R equals 0. If R is positive, then the two variables will increase or decrease together. So positively correlated. And then if R is negative, the two variables are inversely related. So they're negatively correlated. And the closer R is to -1 or 1, the stronger the correlation. And then the closer to 0, the weaker the correlation. So the more kind of a scattered, that it's harder to draw a straight line. Incidence. So this is a proportion of new cases of disease occurring during a specific period of time. And make sure you definitely keep this separate from prevalence. So I don't know if you've already been over this or not in other classes, but incidence is different than prevalence. And that the big difference is incidence and prevalence is that incidence is focused on new cases, versus prevalence has quote unquote existing cases, a proportion of existing cases of a disease during a specific time period. So incidence tells you about the risk of contracting a disease, versus prevalence tells you how widespread the disease is. I like these two. I'd put stars by that. To me, that helps me keep them straight. So diagnostic tests, you guys know about these. You've probably seen the rapid strep test in urgent care clinics. So you guys probably know this, but none of these tests are 100% accurate. So you always need to take that into consideration when you're using them, and when you're looking at research papers and stuff, they should be taking that into account. There's a few ways to do that. So they measure sensitivity, specificity, positive predictive value, and negative predictive value. And here they are, all the definitions here. So sensitivity is the ability basically to identify true positives, where specificity is the ability to identify true negatives. And then the positive predictive value is the probability that individuals who test positive for the disease actually have the disease. So they are, they get a positive, a plus on the test. The screen shows that they have it, and that this positive predictive value shows you how likely it is that they actually have the disease, versus a negative predictive value is then going to be the probability that individuals who test negative for the disease who actually have the disease. So the focus of sensitivity and specificity is on the test, versus these last two, the positive predictive value and negative predictive value, are focused on the patient. So in other words, just to kind of summarize, because students get these mixed up a lot, or they get them kind of, sensitivity is a probability that the test is positive when the disease is pregnant. And then the PPV is a probability that disease is present when the test is positive. And then specificity is the test is negative when the disease is not present. And then with the NPV, the disease is not a probability that the disease is not present when the test is negative. So more patient focused, NPV and PPV. And this is a nice, I think, nice visualization that helps look at the sensitivity, specificity, PPV, NPV, and showing you how to calculate those. And then so basically, is the test positive, yes or no? Disease present, yes or no? And then you can plug in your numbers here, and you can calculate sensitivity, specificity, PPV, and NPV. So that is it for me today, guys. Hope you're having a good summer. I'll talk to you guys later.